Great. Thanks for the introduction and for the opportunity to speak. And thanks everyone in the audience for giving me some of your time tonight for me to talk about what is admittedly a little bit of a tongue-in-cheek title, talking about orbital Legos. This is pretty much me trying to explain how I think about chemistry and using kind of a more qualitative way of thinking about molecular orbital theory to try and decompose more complex molecules. And for that reason, the talk's going to be a little bit segmented. Hang on. There we go. I don't usually do outline slides, but since we're going to be jumping around a little bit, I thought it might be useful to give you guys a lay of the land. So first, I'm going to talk a little bit about molecular orbital theory and sort of define what mixed valency and electronic coupling are, because that'll sort of be the meat of the research. Then I'll go into talking about what I mean by quote-unquote orbital Legos and maybe a more professional way of calling it a molecular orbital fragment approach to looking at electronic structures. Then I'll talk about how I use ferrocene in this sort of, paradigm to look at electronic coupling between metals. And, if we're not going over time, I can talk about how I've used some DFT to sort of bootstrap design of, new systems. So, some people, give molecular orbital theory a bit of a bad reputation, potentially a little bit deservedly so, because it can be quite complicated. I mean, historically in the organic chemistry community, it's not used very often, understandably, because trying to work out the molecular orbital diagram for a natural product would be an absolute nightmare. But even in inorganic chemistry, when you have a high level of symmetry, you can see that very quickly, even for only moderately sized molecules like this cerium metal cluster, the work that goes into solving the molecular orbital manifold ends up being very arduous and pretty much intractable. So, the thing that we need to ask if we want to start using molecular orbital theory for reasonable sized systems, is there a way we can bridge between these two so that we don't throw up our hands and say it's too complicated, but also get some utility out of it as well? And that's pretty much what the thought is for frontier molecular orbital theory, where instead of considering all of the orbitals in all of your atoms, you're just looking at the highest occupied molecular orbital and the lowest unoccupied molecular orbital, since those generally dominate the reactivity, especially in inorganic complexes. And that just reduces the number of things you need to think about, and you can usually get reasonable predictions just by considering the symmetry and energies of the systems that you're looking at. And as a textbook example, you can talk about metal carbonyl compounds, where the carbonyl has a lone pair as its Homo and a pi star system as its Lumo, and those can engage with the metal and balance depending on the properties of the metal. For example, in a more acidic metal, you might deplete that lone pair and activate the carbonyl as an electrophile at carbon. But as you traverse the periodic table and get more basicity in your metal, you could obtain more back bonding into that pi star system and instead activate that oxygen as a nucleophile. So in this way, by just thinking about the relative symmetries of the fragments you're looking at and applying some basic periodic trends, you can get a reasonable prediction about what's going to happen in this type of system. Hang on, I'm just going to turn off my video because my computer is lagging a lot. And we can take this to a bit more of a rigorous place by also adding a layer of thinking about how differences in energy can affect the polarization of a bond. So in a hypothetical bonding scenario where your metal is approximately the same energy as the carbonyl Lumo, you would expect a relatively equal contribution from both fragments in the bonding orbitals between the metal and the carbonyl, as shown here. But if you start going across the periodic table and you take a metal that has the same configuration, but you increase the effective nuclear charge, which then stabilizes your d orbitals, that creates an energy mismatch between the d orbitals and the carbonyl. And as a result, you're going to polarize the resulting bonding orbital more towards the metal than the carbonyl. So this would be the example of a more acidic, poorly back bonding metal, whereas the former would be more of a basic, stronger pi back bonding metal. And while I showed this here in a more concrete molecular orbital diagram, these are properties you can infer from simple periodic trends. So it's something that you can intuit a little bit by just looking at, the generic properties of different areas of the periodic table. So keep that in mind, because we're going to get back to that later in the talk. But now I want to introduce electronic coupling and mixed valency. And I want to pause here for a moment, because I know that these ideas might not be too familiar with everybody in the audience, especially the concept of electronic coupling. So we'll unpack that a little bit. When we talk about different forms of coupling in chemistry, we're just saying that when you have two systems, some perturbation of one system will affect the other. For example, if you're talking about NMR, you have spin-spin coupling, which just means that the energy of one spin is influenced by the orientation of another spin. Here, if we talk about electronic coupling, we're just saying that the electronic state of one site can affect another site. So most commonly, we're talking about two metals. And this can happen through a lot of different mechanisms, and I'm not going to belabor talking about all of them, because only one of them is going to be particularly relevant to this talk, which is like a through bond electron delocalization type mechanism. And what that means in terms of your experimental observations is if you have two metals connected by some sort of conjugated pi symmetric linker, and you take an electron out of the system, you might assume that that positive charge left by oxidation will be borne by one metal. But if you have a sufficient amount of electronic coupling, that positive charge actually delocalizes over the whole system. And what that means is that the chemistry of both metal centers is inextricably linked. They are going to influence each other as they undergo different electronic changes. And anyone who's familiar with electronic coupling and mixed valency will know that there's obviously a lot more to this story, but to keep the scope of the talk in check, we're going to talk about this as a delocalization type picture. And you can split this into three general classes for different mixed valent compounds. Mixed valent compounds being systems where you have two metals in different oxidation states, shown here with M2 and M3. So in the class 1 regime, where you have no electronic coupling between your metals, you can envision that you have molecular orbitals that are predominantly localized on each metal. So this will actually behave like this top system over here. There is no communication between them. And then if you go along this continuum to a class 2 system where there's weak electronic coupling, you can kind of envision that as in the molecular orbitals, there's predominant electron density on one metal, but there's a little bit of contribution from orbitals on the other metal. And an important property that arises from this is that this reduces the barrier for electron transfer. So you can either optically or thermally induce the electrons to hop between these two metals when you have this type of electronic coupling. And then going to the strong coupling limit of a class 3 compound, actually the orbitals are partitioned between the two metals, and if you take an electron out, that charge is equally distributed, and you no longer have metals that are well defined by an integer oxidation state, because, well, each one bears an extra half unit of charge. And in this case, you still get interesting optical phenomena, but it's no longer well categorized as a charge transfer because, well, this, you're not distributing charge between them. It just goes to an interesting excited state that has different properties. And if that, if that still feels a little bit, a little bit to get your head around, you can still look at this through a valence bond type picture. So if you think about two metals, for example, these two ferrocenes linked together, you can imagine pushing your arrows like you would in organic chemistry to push that positive charge all the way through the bridge and onto the other metal. And you can think of the extent of coupling as being how much each of these different resonance structures contributes to the overall resonance hybrid. So if you think about it from that lens, hopefully you can see that a system like this should not have a substantial amount of electronic coupling, because if you think about this in like an organic sense, there's no conjugation through which to push your arrows. So you wouldn't expect that oxidation at one site should influence the other, because you can't get any sort of resonance communication between them. If, on the other hand, you have something that is connected through some sort of conjugate bridge, you can imagine pushing your arrows and getting that positive charge to float between those two metals. But as an inorganic chemist, I can imagine other systems other than carbon p orbitals that would provide a pi symmetric bridge between your two metal sites. You can use another metal. So for example, here you have compound A dimerized across a platinum atom. And when it's dimerized like this, you do in fact see electron coupling between those two ferrocenes, but it's not going in this through bond sigma network, instead going through the pi network through that central platinum. And I think this is a fundamentally interesting way of thinking about these types of systems, because in a purely practical sense, this allows you a form of modularity that's a lot harder to get in organic synthesis, because you can imagine that if your linker is another metal, it's relatively simple to just change what metal salt you throw into the reaction to change the properties of your bridge, whereas in organic synthesis, you would have to synthesize an entire new library of compounds to tune your properties as desired. For example, if you have these two red metals connected by this sort of bluish gray one, you can imagine if this one is a more acidic metal, you would get a hypothetical electron flow towards the center, versus if you have a more basic one in the middle, you can get hypothetical electron flow out to the edges. Furthermore, if you're trying to mix d orbitals with other d orbitals, you get a similar energy fundamentally, since they are of similar orbitals, and also the d orbitals are just more diffuse and radially extended than p orbitals, which kind of does you a couple of favors. And in addition, because they're atomic orbitals rather than molecular orbitals, they have a very predictable symmetry. It's not always obvious what the frontier orbitals of an extended pi system will be, but you pretty much know what the atomic orbitals of a metal looks like, because they are defined by the simple atomic orbitals that we get from quantum mechanics. And lastly, there's just new chemistry that we can think of exploring, because while this sort of regime of looking at how a positive charge can delocalize through metals has been explored for a long time, a more difficult question, one which has still been looked at but is generally hard to get useful systems for, is when you can transmit that electronically coupled system and then add another metal and have that transmit to the third metal as well. So, if you suddenly have three metals and maybe one of these is some sort of reactive metal, are you going to stabilize some sort of new oxidation state? Are you going to get intermetallic cooperativity? Are there potentially interesting molecular electronics or NLO applications that you could get from this? Is there, different photophysics that you could get? These are questions that are somewhat unanswered because there aren't a lot of useful systems that you can look at in this sort of chemical space, just because the design principles and the syntheses end up being very challenging. So to sort of simplify that a little bit and to explain why I keep showing ferrocene as in my slides, is because I find it to be a pretty intuitive model system. And there's a variety of reasons for that. One of the most helpful ones is that it's extremely synthetically accessible. Because ferrocene acts mostly like a naive or a innocent arene. Any sort of organic chemistry you could do on an aryl system, you can do on ferrocene. So Friedel crafts, lithiation, cross-coupling, those all work perfectly fine. And because ferrocene has been studied for so long, pretty much any derivative you want to make has been made at some point, and there's a good synthesis that has been reported in the literature for it. And even more conveniently, a lot of these derivatives or useless synthons are available commercially. Additionally, because there's so many of these different compounds in the literature, any data that you collect, like UV-Vis, IR, NMR, whatever, you can place that in context of other compounds already described in the literature. And another one which pleases me a lot is that it crystallizes extremely well. So some of you may have seen on Twitter that I posted this. This actually happened the other day. I was just collecting column fractions, and by the time I was done with running my column, I already had crystals growing in my tube, and they actually were diffraction quality, albeit weakly diffracting. I got a crystal structure out of that just by collecting the contents of my column. So these things really seem to like to crystallize for one reason or another. And additionally, if you recall from earlier, when I was talking about how energy matching of different systems can have important ramifications on the orbitals, you can kind of do that with ferrocene relatively easily by substituting the CP rings, and that changes your redox properties and your electron driving forces, which can ultimately be important for sort of fine-tuning your system. And lastly, just because the electronic structure is relatively simple and very well understood, allows you to predict with more ease what types of interactions you might observe, and allows you to more easily rationalize whatever data you end up getting, because you can reference back to sort of a known electronic structure and sort of make modifications from there. Now, obviously, I'm not the first person to think about putting redox groups onto a system, but in a lot of literature, especially in catalysis, the arguments that people look for is to attach a redox group to some sort of catalyst, and by toggling the redox state of that redox group, you can increase or decrease the electron density of a metal to elicit different sort of reactivity properties. But more recently in the literature, when people have been talking about so-called redox non-innocent ligands, which are those such as shown here, where the ligand is redox active, and through delocalization of electrons from the metal and through the ligand, we actually get the sort of resonance hybrid that renders the oxidation state somewhere intermediate between whatever you would normally assume. And that's because you have delocalization of electrons from the metal onto the ligand in a much greater degree than you would in a typical coordination compound. And, hopefully this sounds a little bit familiar, because that's kind of exactly what I was talking about with these mixed valence systems. So these redox non-innocent catalysts are really a form of metal organic mixed valency. However, the fields don't directly communicate with each other in a lot of instances and use different vocabulary to describe their phenomena, which I think presents a really interesting opportunity to explore where those two worlds meet and how to sort of rationalize their very similar ways at looking at chemistry. So, for example, if you take some sort of hypothetical this Ferrocene system connected by a pi bridge, and you just make that pi bridge a redox non-innocent complex, you get some sort of new emergent property from this system. For example, we know that this metal is quote unquote electronically coupled to this ligand, and if this organic ligand is electronically coupled to that metal, does that impart three-way communication between all of the metals? That is to say, if you're looking at sort of like a delocalization conduit, do you have something that looks kind of like this in your frontier orbitals? And if so, does that change the chemistry of the system when you start doing redox chemistry at those ferrocenes? Now that's an interesting idea, but it's kind of hard to imagine whether or not that's even a reasonable proposal. So the first thing that I like to do in a situation like this is to start thinking about what the frontier orbitals of these systems might look like, especially since in electrochemistry, the frontier orbitals are the ones that you're generally accessing during redox events, especially when you have metals involved. So kind of like how a synthetic organic chemist might look at bond disconnections for a more complex synthetic target, we can think about molecular orbital disconnections. That is to say, can you find places of the molecule where you kind of know what that fragment looks like in its frontier orbitals? So you might not know what ferrocene is because you don't study it for a job, but this says electronic structure of ferrocene is pretty well understood. So we can say, all right, we can clip those off and say that that's some fragment that we know. And then we can look at the resulting pyridine diimine and say, well, carbonyls are relatively simple. We know what those look like. It's just the pi bond and the pi anti-bond. So we know what that looks like as well. Then we can go to the pyridine and say, well, we know what arenes look like and heteroarenes. So we know what the molecular orbitals on the frontier of pyridine are. And then all of a sudden we have each of these fragments are understood in their own way. And if we overlap their frontier orbitals, for example, up here with all of their Lumos overlapped and down here with all of their Homos overlapped, I apologize that I got cut off. But you can sort of see that all these orbitals are appropriate symmetry to overlap with each other. And that gives you, a suggestion that maybe this is a system that, could work out because you at least have the right symmetry for everything to interact. The harder question is whether or not, the bonding interactions will be strong enough to actually produce the properties you want. So as I say, we sort of deconstructed this into fragments. So this is the quote unquote orbital Lego approach that I sort of reference in the title. That just kind of gives you like a first order approximation of whether or not your suggestion is even reasonable. And this isn't so different in concept. Obviously, it's not theoretically rigorous in the same way, but in your inorganic chemistry class, you may have learned about how to do linear combinations of atomic orbitals to build MO diagrams. And this is somewhat similar in spirit, but using molecular fragments instead of, atomic orbitals as your Lego set, so to speak. All right, so we've kind of said this looks like an interesting or promising target. There's at least some reason to think that this could work. So we have to go about making it. Fortunately, all these syntheses are relatively well behaved. So the first step, which is always the most fun, the most spicy, is making iodoferrocene from ferrocene. And that's just done with lithiation with T-butyl butoxide, and you chuck a bunch of iodine at it at -78. And as far as I can tell, the scale works as high as you're willing to sling the T-butyl into the reaction. For my own personal safety and sanity, I generally keep it to 8 to 10 grams because I'm already using entire bottles at that point. And then you can aminate that with aqueous ammonia and then an iron oxide copper iodide catalyst system and under pressure and ethanol to get the aminoferrocene. And that's the most convenient way to do this, but I'm going to show a second one just because I think that the chemistry here is really cool. So, another common way to make amines is through Gabriel synthesis with a phthalimide reagent. So you have to make the ferrocene phthalimide, which you might think that you could do a more traditional sense, but if you chuck copper and phthalimide salts in with iodoferrocene in solution, you instead get biferrocene as a cross-coupled product. So instead, what you have to do is react in the solid state with a preformed copper phthalimide in order to make the ferrocene phthalimide. And this works really interestingly because iodoferrocene melts at 140 C, so actually acts as a flux for the solid state reaction. So it's really an interesting reaction to perform and to see, but unfortunately this pathway ends up being a little bit unwieldy for logistical issues, even though the chemistry generally works fine. So then when you have the amine, the last thing is just to do an imine condensation. You start with a slight excess of your amine and you do it with this commercially available diacetylpyridine. And you start with a pale orange solution from the ferrocene and you cook it with some acid and some heat. And you end up with a very deep blood red ligand, which generally works pretty well. You can get higher yields if you want, but the product crashes out as crystals, which is very convenient. You can process the supernatant for more if you desire. And you can kind of see that here, this very deep red solution with nice little microcrystals that form over the course of the reaction. Then the next step is to chuck a metal inside that binding pocket, and you can do that with a variety of different metal dichloride salts. And something that's really cool about this chemistry is you can just watch reaction progression by color. So you can tell this reaction is working when it starts turning red, and you can see this one's working when you start seeing blue crystals crash out of solution. But this sort of poses an interesting question, because usually in coordination compounds, the color comes from some sort of metal D transition, d orbital transition. And looking at these different metals that I've put in there, iron, cobalt, zinc, magnesium, they're all very different in both their electron configuration and their coordination chemistry. So you wouldn't expect them all to, result in the same color complex. So that suggests that, it's not the actual central metal that's providing this color. Instead, it's the ferrocenes. And that realization actually has some really interesting ramifications, because as I mentioned before, the electronic structure of ferrocene is pretty well understood. And so here, I've shown sort of the frontier orbital manifold for ferrocene. And you get like this, this weak transition at like 440 nanometers. And it's symmetry forbidden, so that's why it's comparatively weak compared to other coordination compounds. And it's relatively narrow because it's a pretty pure D to D transition. And, again, it's relatively insensitive to CP substitution. So ferrocene derivatives are generally orangey, to say the least. But what that means is that if you see a change in the color, you're directly processing or probing changes in the orbitals or the symmetry of those, the energy or the symmetry of those orbitals. So if you see a change in the intensity, that means that you've broken the symmetry of this transition. You see increases in the width, that means that there's more delocalization in either the donor or the acceptor orbital. And you see a change in energy, that means that you're changing the relative energies of these areas. So the UViz actually has some interesting information it can provide to you. So we can, go ahead and do those experiments. And I apologize, this figure is a little bit busy, but I'll walk you through it. So here down at the very bottom, there's aminoferrocene. You can see that it's pretty weak compared to everything else. And you can see it's comparatively narrow when I have this inset. And so if you take aminoferrocene and you put it into this ligand, you see immediately it dramatically increases in intensity, and it also broadens out and also redshifts a little bit. So that's an indication that this is no longer a pure D-to-D transition. It has some sort of charge transfer character, and there's some form of delocalization due to how much it's broadened out. And by adding that extra metal to the coordination sphere, you also get a further broadening and redshifting of that signal. So that's suggesting to us that one, that central metal probably isn't directly involved in any of these transitions. Otherwise, we'd probably see more of a change in the the character of those bands between all these different metals. And I'm not going to belabor how we came to this conclusion, but just to sort of get to the meat of it. The coordination helps promote mixing of the imine pi star system and the ferrocene Lumo. So basically, this is a Homo Lumo transition, and the Lumo is where all of the interesting delocalization is happening. But the central metal dichloride fragment doesn't seem to be participating directly in this. So that's kind of cool. It's kind of interesting. We learned something about the orbital symmetries and such, but it doesn't actually tell us much or really anything about whether or not there's an electronic coupling in the system. So the first experiment that is usually done to probe that is to do cyclic voltammetry. The reason why this works is because if you have two metals that are related by symmetry, so they have the same sort of coordination environment, if they're not coupled at all, that means one metal doesn't care that the other one's been oxidized. You should expect that they should have the same oxidation potential, and you would get a single redox wave that accounts for 2 electrons. If instead they're electronically coupled, so that positive charge can sort of delocalize throughout the system, then you should expect to see a split redox wave, and the degree of splitting between those waves can be correlated, but not absolutely related to the degree of electronic coupling. So this ends up being a really useful, quick, easy litmus test for whether or not there's electronic coupling. So we can go ahead and do that experiment as well, where here is just an internal standard. And if you take just like that free ligand and do the CV, you see that there is indeed just one redox wave. So there's not really a substantial degree of electronic coupling here. But instead, if we look at any of these coordination compounds, you see that they all have a very similar CV to them. They're all shifted, or rather the splitting is approximately 200 millivolts between each wave. And the first wave occurs at pretty much the same energy or the same potential as the free ligand, which also coincides roughly with the redox potential of ferrocene itself. So that tells us that the energy of the ferrocene iron, the frontier orbital there, is not really substantially different from normal ferrocene, which is how we sort of came to the conclusion that the delocalization wasn't happening in those occupied ferrocene orbitals. So that's also kind of odd that these all behave so similarly, just like we did in the UV vis. Before going on to the next thing, I just want to point out that these are irreversible CV waves, because upon reduction, you kick out a chloride from the metal chloride, and then it chews up the DCM solvent to regain its chloride. So that's why these are sort of, you don't get a return wave. If you scan sufficiently fast, you sort of recover a quasi-reversible behavior, but that's not sort of the interesting part of this voltammogram. So we have a sort of a proposition for what's going on in the system, and we can turn to DFT to try and see if we can corroborate that, and it turns out that it does. So if you look at the HOMO of all of these compounds, you see that they're predominantly based on the ferrocene d orbitals, and this is actually the same d orbital that is the HOMO of regular ferrocene, so that tracks. And the LUMO of all these compounds all feature predominantly the pi system of the organic pyridine diimine backbone, with a little bit of contribution from the ferrocenes. And notably, in all of these, there's not really any substantial contribution from the central metal. So that kind of really lines up well with all of those previous experimental findings, which is that there is some sort of increased delocalization in the excited state. The ground state is pretty much just normal ferrocene. But that also means that, it seems like this needs to be coordinated to something. It doesn't really matter what. So kind of an interesting experiment that I did is if you take the ligand and you just chuck some acid at it, in this case in the form of H-barf, you get a very similar phenomenon. It starts changing color, and you get a nice little isobestic curve if you titrate it in as well. So it's a really interesting, neat system that you can sort of see. So now the question is, all right, that's all interesting and everything, but what does this kind of mean for the chemistry going on here? So to bring this back to like an MO picture type of place, we can compare the proposed molecular orbitals for all of these systems. So here we have just normal ferrocene. Then we have this pyridine diamine bisferrocene ligand. And well, we know that the Lumo drops in energy and it broadens out through mixing of the ferrocene Lumo with the PDI Lumo. So that, makes sense here. We have these excitations where two lines are drawn because it's known that single band actually has two transitions in it. And then when you coordinate that to another metal, that further stabilizes the organic pi system. And now that they're sort of more close in energy, you have a greater degree of delocalization and equal contribution, which further lowers that in energy and further broadens out and delocalizes the system, which is kind of an interesting realization, especially again, since the identity of this thing doesn't really matter. I anecdotally have evidence that I get similar chemistry if I add sodium chloride to it or sodium sulfate. It doesn't metallate very much, but you see the sodium chloride start turning purple, which is kind of cool. That it really doesn't seem to care what you put in there. All right, so I said earlier that cyclical voltammetry is a useful tool, but is not a definitive tool. There are some false flags that you can get, or false positives from CV. So the more important characterization is to do spectroelectrochemistry, where what this experiment entails is you're doing bulk electrolysis. So you're doing oxidation on your system in this case, and then you're taking UV-vis spectra as you're doing oxidation. So what's interesting here is that this free ligand, we can't stop after one oxidation, because recall within the cyclic voltammetry, there's one single wave, both ferrocenes oxidize at the same potential. So if electrolysis continues into two electrons are ripped out, and then the current stops. And when you sort of look at the change in the UV-vis, you see that this feature right here in black, which is the starting neutral state, it plummets. You can see that in this different spectra here in the red dashed line. So that further confirms that the donor orbital in this like ferrocene transition is ferrocene based, because you take the electrons out of ferrocene and you don't have a band anymore. And then you see a growth of a ferrocenium ligand to metal charge transfer. And for everyone wondering what all this garbage is, it's they're like solvent overtones and such that appear in the near IR. Our lab doesn't have the fancy spectroelectrochemical equipment to not have those in our spectra, but they, as you can see, they subtract out fine. All right, so that's cool. We basically just rehashed what we already saw with the CV, which is this is a non-electronically coupled system. It's a class 1 system. But if we take our iron dichloride complex and you rip one electron out of the system, what you instead see is this incredibly broad feature in the near IR. Again, you can see that in this different spectrum most clearly, and that's indicative of a metal-to-metal charge transfer in the system, which is telling us that there is a degree of coupling, because if you recall from the beginning, when there is a degree of electronic coupling, that creates a low barrier to electron transfer. So, and that means that using adaptations of Marcus theory, you can sort of back out the degree of electronic coupling from the features of this band. And deconvoluting this mess is not trivial, but if you sort of do a rough fitting of this, you get that it's a degree of coupling that fits to a weak to moderate class 2 compound. So nothing to go shouting home about in terms of strongly electronically coupled systems, but it is interesting that this central metal seems to be very important for observing that coupling, and it acts as a switch, but doesn't actually participate directly in that system, which I find to be kind of an interesting phenomenon. And just kind of to drive the point home, if you rip another electron out, so go to you take the electrons out of both ferrocenes, you see that very broad metal-metal charge transfer feature go away, and you also see the rest of the ferrocene like metal-ligand charge transfer go away as well. So that further reinforces that this electronic coupling is happening between the ferrocenes and not between the ferrocenes and that central ion dichloride, which we already kind of intuited from our other data. But here's things where maybe I'm going to say something a little bit controversial, but I do believe that eyeball spectroscopy does count for something. If critically, if you know what your transitions are, it can count for something. So you can see here, this is that metal or iron dichloride complex that I started with. You can see it's a nice blue color. When you oxidize it by one electron, it turns black because that really broad near IR feature bleeds into the visible, and basically the entire 300 to 3000 nanometer range is absorbing, and it's black not because it's optically dense, but because the color is simply black. Continue by another electron, and the black goes away because the metal-metal charge transfer goes away, and you get this sort of weird yellow-green color. So this is just kind of a fun quirk of doing these types of experiments where the transitions do correlate to very specific electronic properties that you can track. And when the color changes are stark enough, you actually do, you can run a reaction. For example, if I'm trying to oxidize this chemically, if it doesn't change color, I know for sure I'm not getting what I want. But anyway, so we've done these in situ experiments to sort of measure the UV-vis spectra in electrochemistry, but it'd be great if we could isolate these things for further study. But that ends up being a bit of a problem, because while you can oxidize this by one electron with acetylferrocenium barf, which has the right potential to sort of thread the needle between a single oxidation event and two oxidation events, you do get a black solution. And if you try and crystallize that solution, what you instead crystallize is the dication. So I only oxidize by one electron, but instead I have the doubly oxidized species that grows crystals. And at first I thought that was just a fluke. Maybe I did something wrong, but then I grew another crystal the exact same way, and I still got the doubly oxidized species. And anyone who's worked with redox active compounds might know where this is going. And it's that, at equilibrium, especially when your split between the two oxidation events is only 200 millivolts, there is a small equilibrium amount of disproportionation that's going to happen. So the only reasonable explanation I can come up with this is that some small amount disproportionates and produces back the neutral compound and the doubly oxidized compound. And while this is extremely soluble, this apparently is not, and over time crystallizes, which drives this forward at least enough to grow some tiny little needles, which is where I got these crystal structures from. And this presents a bit of a problem, because if this is always going to be less soluble than this, growing crystals of this is going to be challenging. And you might think that I can stack things in my favor by changing the counter ion, which is true, but the problem is that if you change from anything other than barf, the solubility tanks and just becomes brick dust. But you can exploit that a little bit through some clever crystal growth. So, for example, here I have a concentrated solution of the neutral compound. And then if you layer silver PF6 on top of it, the mixing and reaction rate will be so slow due to the narrow interface that it actually crashes, or the reaction precipitates out as crystals. So it's able to grow single crystals of the PF6 singly oxidized cobalt species, which I definitely did not expect this to work. I was just reaching the end of my rope and decided to try it, and somehow it still worked. So just kind of gives credence to the fact that crystallography is half perspiration and half inspiration, I suppose. But there's an interesting structural change that you see across the series. So, you have this relatively coplanar arrangement in this sort of neutral compound. You oxidize it by 1 electron, and it looks mostly the same, but you can see this ferrocene sort of bends in, and it's not super obvious from the way that the unit cell is constructed, but this PF6 is actually ion pairing with this. It's just, outside the other unit cell. It's a lot more easy to see when you do the packing diagram, but this is the oxidized ferrocene, or the ferrocenium, I should say. Then we oxidize it by another electron. You see that both of them do that, which is odd. And if you go ahead and try and do a DFT calculation, like a geometry optimization, you see exactly the same thing, that one of the ferrocenes will bend inwards, and if you do it by 2 electrons, both of them do. Now, a single determinantal method like DFT isn't going to capture the electronics of this in a particularly good way. So I don't necessarily trust the electronic structure calculations of a lot of that, but geometries mirror the crystal structures reasonably well, which is kind of interesting because they started as symmetry-related metal centers, but then, suddenly they aren't. And, we're still thinking about why that might be. It's, maybe these chlorides are interacting, perhaps in an electrostatic way to help stabilize, because when these things bend inwards, they get a little bit closer to the chlorides if you sort of measure those. So that's kind of where that project left off. That was sort of the publishable unit that we put out into the world, which left me thinking, all right, what now? What do we do with all this knowledge that we gained from the previous project? Because transition metals have a lot of really interesting redox properties that make studies like this really interesting, but it also makes it complicated, and deconvoluting, what's coming from the ferrocene, what's coming from the transition metal is hard. Even if the answer is it's all coming from the ferrocenes, there's a lot of controls you have to do in order to make that designation. But an interesting observation you can make is if you move towards the less redox flexible lanthanide series, you can isolate the size and charge effects from, for example, the coordination chemistry, and also from the redox participation. So you sort of get 3 axes that you can move along to sort of explore the space. For example, going from scandium, which behaves more innocently like a transition metal, to yttrium, to lanthanum, you're sort of decreasing the amount of covalent character in those bonds. And I recognize these are not lanthanides; they're rare earths, but they kind of have similar coordination chemistry. Similarly, you can go from lanthanum, which doesn't really have readily accessible redox chemistry. Obviously, it is possible, but it takes some. You have to hit it with a sledgehammer. Whereas cerium and samarium have, in cerium's case, oxidation chemistry that still takes some driving force, but you can commercially buy cerium-4, and you can buy commercially samarium-2. So these are, redox couples are at least within reasonable tractability. And sort of looking at those different axes that you can explore the space in, it sort of kind of asks this question. So if we bring this back to this diagram that I had at the beginning, if you have a redox inert metal that is sort of coordinated to a mixed valent ligand, how does that change versus if you have a more redox flexible metal? Does that mean that, for example, if this metal has some degree of oxidation chemistry, can it participate more fully in the process? Does it not matter? If you change how charged dense it is, does that change how much it does or does not stabilize the pi system and change the energy match, which apparently was important in the the transition metal case? That's kind of the chain of thought that I started tugging on. And other people have looked at redox active ligands with lanthanides. Some people have built half of their career around it. Suzanne Bart actually took this pyridine diamine ligand and chucked it at neodymium and reduced it and looked at those properties. It mostly was just a reduced ligand on neodymium. But she also had this other really interesting system with this sort of aryl oxyamine compound, which if you throw sulfur at it, the redox equivalents inside of these ligands actually allowed the neodymium to undergo oxidative addition into the sulfur ring to make this metallocycle, which was a really neat sort of proof of concept that having redox active ligands with lanthanides can do something interesting when in the right position. And also the Evans group, makes lots of very wonky strange lanthanide compounds and oxidation states they don't expect. And one notable example, at least in my opinion, is this system where this sort of tripodal aryloxy compound, if you hit it with KC8, depending on which lanthanide you have in there, you can get reduction of the ligand or reduction of the, hang on one moment. Let me mute some stuff since there's a lot going on. All right. So yeah, depending on which lanthanides you put in there, you can get, different redox events at different locations. For example, you aren't generally going to reduce lanthanum or cerium. In those cases, you get reduction of the, the ligand, and more easily reduced lanthanides, you actually do get reduction of the lanthanide. So I think that's kind of an interesting sort of observation as well. And that sort of brings me to sort of adapting my system to try and be with lanthanides. And in this case, we have to sort of change from a pyridine to a pyrrole, because one of the issues that was seen when people tried to put lanthanides inside of the pyridine diamine system is that the neutral end donors just don't really hold on to the lanthanides quite as well as you would like. But also, if you sort of compute the frontier orbitals here, they're markedly more delocalized in both the Homo and the Lumo than the pyridine system. So if the lessons we learned from the previous project are generalizable, then this makes this actually a pretty promising thing to try and study. So I spent a lot of time in my first year trying to make this gosh darn thing. There's a very old preparation for these types of compounds that involves making these sort of masked diacyl pyrroles, and then you sort of oxidize off and deprotect them with mercury and HBF4. Unfortunately, it just doesn't really seem to work very well, at least in my hands. Maybe I was just a dumb first year, but the first deprotection goes fine, and the second one just turns to utter garbage. It turns into this really disgusting, muddy brown mercury sludge. I think I did this once or twice and then realized I was generating super stoichiometric mercury waste, and I was making organomercury intermediates in DMSO, and it didn't really work. And I think I literally just took the flask and dropped it into a waste bin and said, not getting cancer is worth more than making this ligand. But I kept looking in the literature, and I found other reports of similar compounds. For example, you might, if you're in inorganic chemistry, you might say, well, why don't you try lithiating it and then doing it that way? And something like that has been done before. This was actually published in Nature Methods. So I thought, all right, Nature Methods, that should probably work. They do mention that this is a tricky reaction, but they didn't quite mention how unstable this intermediate is. I think something about if it goes above somewhere around -40, -50 degrees Celsius, it just turns to black garbage and starts cleaving off the Bach and polymerizing and becomes an utter mess. Also, the lithiation step doesn't work fabulously also, which I looked at through deuterium labeling. But hopefully you can all, laugh at my hubris, because, trying to keep this entire system at below -40, I was trying to do this dropwise cannula transfer stuffed with dry ice, which was about as much of a nightmare as you would think it would be. So at this point, I was getting a little bit, I was looking out to other opportunities. I thought, okay, what if we do some sort of bromination instead to help with that lithiation step? But you can brominate this, but if anyone has worked with conjugated polymers, pyrrole really likes to polymerize, and unfortunately dibromopyrrole also really loves to polymerize, so that also wasn't very good. I went to this really obscure French journal which claimed you could make this just with zinc powder and K-carb. Well, that also didn't work, which, I was kind of swinging for the fences at that point. But fortunately, recently, the Anderson group reported what was actually a very similar route to what I was originally doing, but that last step instead is with peroxide instead of mercury, which made it a much nicer method. While I don't relish concentrated peroxide, it's better than super stoichiometric mercury. So then the question just becomes, can you do this last step? And, again, in my foolishness, I said, oh, that's just an imine condensation. That's fine. All these steps work fine. This can't possibly be the problem. It turns out this ends up being a little bit more challenging than I thought it would be. You can get this, so I use this as like my model to try and dial in the conditions. Fortunately, you can't just cook them together like I did with the pyridine system to get it to work. You only get traces of, product out. But if you do it under Dean Stark, you can get it to work in a reasonable amount of yield. So clearly it's just equilibrium's the problem. Get the water out and everything works. That's fine and dandy. But then you do it with the diacetylpyrrole, and then it just still doesn't want to go forward, which is very unfortunate. But then if you read the Anderson paper a little bit more carefully, you realize that this clearly was a problem that they had as well. And it's not surprising that this reaction doesn't go, because if you look at these conditions, they run it in neat cyclohexylamine. So clearly they're pushing that equilibrium forward as hard as they can by just running it neat in the amine. So unfortunately, I can't do that because aminoferrocene is a sublimable solid. But there's other tricks you can play. Poor equilibria is not something that should fundamentally hinder a good reaction. So the Stoltz group reported this nifty little modification where if you're trying to do a reaction on a reasonably small scale where a Dean Stark isn't terribly effective, you can just stuff an addition funnel with sieves and let your solvent reflux up the side arm and then percolate through the sieves. And that works, it works as well as I need it to. So you can take, an excess of amine with some acid and just like let that rip for 5 days and you get enough. This is intermediate, so you can also just chuck that back into the reaction, let it keep going. But 45% after chromatography, you know what? If we can also isolate the intermediate, I'm happy with that. And fortunately, the reaction also works pretty cleanly. As you can see, I got crystals, and this is fresh, hot off the presses today. I got the crystal structure from the crystallographer, so that was a really nice result to wake up to today. But all this while, I was also looking at what is obviously the goal here, which is to actually try and metallate it. And unfortunately, what works for transition metals just doesn't work very well for the lanthanides, which so any of you out there who's worked with the lanthanides will not surprise you terribly. But if you try and metallate, your ligand and try and do a salt metathesis, unfortunately, the reaction clearly starts going forward, but you get this incredibly insoluble red brick dust. Everything in the reaction, excluding the chlorides, are extremely soluble, and the chlorides are at least somewhat soluble. So it's kind of unclear what's going on here. If I had read my literature a little bit more carefully, I would know that this is probably not the product I should expect. But instead, in the literature, related compounds end up making these, these bridged compounds, which is quite common for the lanthanides. So I should have predicted that. So I'm currently on my way to, resolve this problem. But that's kind of the state that I'm at now, is trying to figure out how to prevent them from bridging, actually getting soluble products. So now I'm going to switch gears a little bit and talk about screening new systems. See, we're going a little late, so I'm actually going to skip through this because this is not too terribly important. Yeah, well, I'll go through this quickly. Basically, this idea that you can use, predictions of your frontier orbitals to, sort of get the properties you want is really interesting in prototyping new compounds. So, for example, this dipyridyl pyrrole system is something that has been explored in the literature, especially in some catalysis studies. But it's still comparatively new ligand compared to other things that people use for catalysis. So this coordination chemistry is still, somewhat being explored. But what's kind of interesting here is, if you compute the frontier orbitals, what you notice is that the HOMO and the LUMO localize in different locations. So for example, if you were to substitute something on this position, you would expect it to have a more significant impact on the occupied HOMO, versus if you substitute it here, you would expect to have a comparatively smaller effect, maybe a simple inductive effect. And then same in the LUMO, this position isn't going to impact the LUMO very much, or at least you would think, whereas these might. And, if I go ahead and do, I beep boop on the computer and do what I do best, which is just chuck ferrocene at things, you can sort of see that at least the DFT supports that, somewhat naive assumption where if you substitute this position, which is where the free ligand HOMO localizes, you do get delocalization and contribution from both centers. Whereas here, if you sort of add the ferrocene where there isn't contribution to HOMO, you don't really get ferrocene contribution. And if you were just doing synthesis and you saw impact versus not impact, you might conclude if you had picked this product that your hypothesis was wrong. But really, based off of the chemistry involved, that does support your hypothesis, even though it's a negative result. But in science, negative results can still support your hypothesis if it's at least not as long as it's disproving your hypothesis. So it just kind of gives you a way that you can rapidly prototype things if you have some idea of what your frontier orbital manifolds look like if you're looking for some specific impact. So with that, I'm just going to conclude. So hopefully I convinced you that you can compose larger molecules in smaller fragments. That helps you sort of understand what you're looking at. Eyeball spectroscopy can sometimes be useful, and looking for similarities in different bodies of research can be an interesting place of looking for new chemistry. So, if anyone wants to stay in touch or learn more about what I do, feel free to follow me on Twitter. If anyone, would like to get advice or perspective or help, just let me know. I've only gotten this far in grad school or, in science at all because a lot of people ahead of me have helped me. And if I'm in a position to help other people, I would be, I'd be glad to. So with that, I'd like to acknowledge my group, including Yossi, who did the DFT for the original pyridine diamine system. All the other ones I did. Rachel Dickin has helped me a lot with thinking about how to do the organic chemistry. Jake Rothbaum, he's just generally a very excitable puppy that really hypes everyone up. Andrew Rosen has also helped me a lot with learning how to do DFT calculations, and obviously my advisor, Tobin Marks, for supporting me in this work. And with that, I'll take any questions.
All right, that was fantastic talk, and we do have a ton of questions. So I think we will just go ahead and jump straight into it. So I gotta say, I know Craig. That's right, Craig. I'm going with CREG. He started. He like said. I told him that he started. He woke up and decided to choose violence today. So let's just go ahead and get right to it. If ferrocene is a sandwich complex, is it also a hot dog complex?
I would say it's not a hot dog complex, but and some metallocenes could be a hot dog complex. Because a hot dog is a subset of sandwich. Not all sandwiches are hot dogs.
Okay. All right.
We'll keep it diplomatic here.
That is very diplomatic of you. I like that. Let's see. Okay, so Dr. Kothapali wanted to know if does this mean that F block elements will have more delocalization than the elements of D block?
Sorry, can you repeat that question?
Yeah, no problem. She wanted to know if F block elements will have more delocalization than the elements of D block.
Well, I mean, that's kind of the question I'm trying to get at.
Okay.
Because, I mean, as I saw with sort of the earlier work, sometimes the property of the metal are, sometimes they do matter, sometimes they don't. So sort of going to a different part of the PR table lets us explore sort of different aspects of those interactions. So we might find that they work better. Maybe they don't work at all. I mean, F elements, or at least the lanthanides, are generally not very covalent in their bonding. So you're not probably going to expect a lot of, like, for example, delocalization onto the lanthanide. You might see that more with the actinides, but it might modify the properties of the ligand in a different way than the transition metals or the p-block elements might, which is kind of the interesting thing I want to look at.
Okay. If the valence of the metal drops to 0, does that mean that the metal will fall out of the organic scaffold? I hope I asked that correctly.
I mean, I think that's going to depend on the the character of the ligand. So in a system like mine, I think it would still stay in because a lot of Paul Chiric's work has been working with like pseudo zero valent iron and cobalt and stuff, where they take a 2+ metal and then hit it with 2 equivalents of reducing agents. So you putatively have a zero valent iron. It ends up being that it's not like truly zero valent, but for the chemistry involved, it becomes zero valent.
Yeah.
So the question might be better put: can you achieve a zero valent system when everything is so delocalized? I mean, you put on your tinfoil hat and say, what do oxidation states even mean at that point?
Okay, fair enough. Let's see. Does the difference in iron charge affect the molecular shape and the way the two complexes interact with the pi bridge?
I'm going to assume that they mean, like in my systems, like there's an iron in the center. I mean, I would think that there would be some impact. What direction that would be, I'm not sure. I mean, you get a bit of a charge balancing problem. For example, if you have iron 3 chloride, you have 3 chlorides, around that central iron. So then that ends up being a bit of a different structure to begin with. So I would have to think about what one might expect from that.
Okay. So Holly Wars wants to know does the color change not being related to the metal mean that the Homo Lumo gap is not metal centered?
Yeah, I mean that seems to be what we were seeing. I mean, there's some small impact. There's a little bit of wiggling between the different bands, but it didn't really seem like there was a large amount of metal character in the Homo and the Lumo.
Okay. What color or colors are the metal complexes with the PDI ligand without the ferrocene moieties?
Those depend a lot more on what metal you have in there. Okay. I'm trying to remember. So I think a lot of them are like green and yellow. I think the ligand itself is usually something like a pale yellow, and then when you add a metal, then you have more of like a charge transfer between that central metal and the pi star system. So I think that becomes more dominated by the metal, and also the oxidation state of the overall compound.
Okay. Rox9194 wanted to know if you've tried reducing the imine to compare your delocalization instead. Not sure what. I don't remember when that was from, but
yeah, that's a good question. I mean, hypothetically, that shouldn't be a difficult experiment. I mean, reducing. I think there were some papers that showed that if you just like sodium borohydride would do it. So it's definitely something I could try if I wanted to sort of drive that nail in the coffin a bit deeper.
Sure. Okay. Okay, this is one I had. Are metals with multiple stable valencies more difficult to model with the method that you're talking about? So I don't know if something like manganese really complex as well with a lot of what you're working with, but it can exist in 2, 3, 4+, reasonably stably. Is something like that a little more difficult to work with?
Yeah, I think that would be a lot more challenging to deconvolute what's going on. I know some people have made similar compounds, just like with like a, not with ferrocene, and they were able to get some interesting chemistry out of that. But I think trying to figure out like the oxidation state and the spin state would be, a little bit less trivial.
Okay. Dan Kurtz wants to know on slide 23, do you think that the peak at about 550 nanometers simply broadens, or are there other peaks growing in on either side? He thinks it was a bit neat looking.
That is a really good question, which I only have a proposed answer to. Okay. So I think you're talking about this blue peak here.
Yeah.
So my understanding, so this is really getting towards the edge of my understanding of mixed valency and electronic coupling, but in the specific mechanism of electronic coupling present in this system, where the delocalization is more in the unoccupied orbitals than the occupied orbitals, you get an interesting phenomenon where you get an increase in intensity and also a broadening of that feature that gives rise to the sort of the electron transfer. So it's like the the intensity goes down because you're removing one of the ferrocenes, but then it's also compensated by it going back up. So that's why you see a bit of a dip, but not much.
Okay.
That's what I think. But someone who knows more about the the photophysics of and the electron transfer chemistry in these systems would be able to speak more intelligently about it.
Okay. This was one that I think a lot of people had this question. On the UV Vis cuvettes that you had, what was that bulb?
Yeah. So this actually isn't my this is not my cuvette. As I said, my lab does not have spec equipment. So we worked with another lab at Northwestern, the Wazalewski lab. So my understanding is that the purpose of this bulb is that you can put like solvents in there and then freeze pump thaw them to get the gases out before tilting it over to get it into the cuvette.
Okay.
I think that's what it's for, because off here on the handle is actually a ground glass joint, so you can put onto a vacuum line to do whatever.
Okay. All right. That makes sense. Okay, so Krieg it wants to know if you started with 1,3-diiodoferrocene and substituted the PDI ligand onto both sides, do you think you could make an extended conjugated polymer? And he thinks that could have interesting properties.
That is a really good idea, and that's actually something I very briefly discussed with a friend. I'm not going to do this at this stage of my PhD, so if someone wants to steal that idea, go ahead. But if you instead made a 1,1 prime diiodoferrocene, so each CP ring has an iodine on it, then you try and do like try and make like a cough or a moth or something like that. You could call it a molecular hinge and get into like nature or something like that. Just because the buzzword would be so appropriate. But yeah, I think that would be interesting. I just I didn't have the bandwidth to actually explore it.
That's fair. Yeah, he actually followed up and said, "P.S. Sorry, I know you hate polymer chemistry."
It's a genuinely good idea. I just if it doesn't go into solution, I don't want it.
Fair. That is perfectly fair. Kim Kissel wanted to know, when you say planar on slide 28, are you referring to the plane with the top of the ferrocene?
Yes. So, the CP ring and then the rest of this backbone and then the other CP ring are roughly planar with each other.
Okay. Dr. Kothpali also wanted to ask if you could try to use a stereoisomer and then try and see if the change in the stereochemistry results in your reaction going faster. This is towards the end of the talk. I'm not sure exactly which reaction she was referring to. It was somewhere towards the end.
Yeah, I don't know. I mean, these aren't like stereochemically active, but I mean, you could imagine, like, for example, at one of these positions are relatively easy to substitute. So, you could do that. I don't know what impact that would have. I mean, you would probably end up breaking the symmetry between the two ferrocenes. So whether or not that influences the chemistry that happens between them, or whatever oxidation, like I assume they're trying to talk about trying to trap this instead of crystallizing that.
Oh, she says it's the one that you showed that takes 5 days.
Oh, I see.
Yeah, that makes more sense.
Yeah, I was like, I'm a little bit confused.
Yeah.
All right. So now that, can you say the question again?
Yeah, absolutely. Could you use a stereoisomer and see if that change in the stereochemistry resulted in your reaction going faster?
I'm not really sure what impact that would have. If they have a specific idea, they're welcome to reach out to me. Seems to me like it's mostly just like there's just a kinetic barrier, because this is a paratoluene group, so there is this ketone isn't particularly electrophilic. So, I mean, I'm definitely looking for ways to speed this up, because twiddling my thumbs and using my hot plate for one reaction over the course of 4 days is not great.
Yeah.
But yeah, if there was a way to do that with some sort of like chiral process, that would be interesting. I'm not very familiar with that.
Okay. Rama, if you want to get in touch. Oh, okay. She said this is a biochemist asking inorganic questions. It might be completely wrong. So, okay. So the last one we have, unless somebody else jumps in with one, is questionable metal. Wanted to know how many of the air-free cuvettes, the freeze pump thaw ones, I think with the bulbs that you had, have you broken over your grad student career?
Fortunately, just one. It was actually very unfortunate. So if you didn't see, it was like a 2 millimeter cuvette or something like that. So, or 0.2 centimeter cuvette. So very thin. I think I just put it down on the glove box floor and it formed a tiny little crack.
Oh, that's the worst.
It still held the solution, but it was just enough that I didn't hold vacuum anymore. So that was like a $500 cuvette that I had to replace. But it happens.
Yeah, it does. Rest assured, I have broken many things in my days. many things. Oh, goodness. All right, so I think if there's any final questions, go ahead and get them in. I'll start wrapping things up a little bit here. But this doesn't mean you can't ask more questions, so certainly feel free to do so. I do want to thank everybody. Oh, wait, there we go. Not sure what it could do, but have you tried abstracting chlorides from your ferrocene PDI iron dichloride complexes?
I didn't intentionally try. I realized after trying the oxidation with silver salts that I was really rolling a dice of whether or not I would get oxidation or chloride abstraction. But it didn't seem like the chloride did it, but other abstracting agents might. Like, I don't know, if I really didn't care for my personal safety, I could try thallium salts and potentially get that off, which could be interesting. I'm not quite sure what that would do, but that would be something to try.
Okay. Again, any final questions, certainly feel free to get them in. But I do want to thank Cole for a fantastic talk. Like I said, that was super interesting. An area that I am completely unfamiliar with, and now have a much better knowledge of. And I'd like to thank all of your friends that came out as well. Chat was very entertaining tonight. I hope you guys will come back again and again. I would also like to say that we are always looking for more presenters. So if any of you who are new tonight would like to do a talk like Cole did, please feel free to get in touch with me. You can send me a PM on Twitter or on Twitch. I'm on Twitter at Meekins Lab, MEEKINSLAB, all one word. We also have the Discord. I'll drop the link again for anybody that joined late. You're very welcome to join that as well. It is a fun and friendly place, just like the stream. But again, Cole, it was a fantastic talk. That was both entertaining and informative, which is, can't really ask for better than that. And so I will say thank you again to everybody for coming out. Cole, if I could get you to hang around for just a couple minutes, we'll talk real quick, and then I'll let you go. But we will hopefully be back next week. Don't have a talk lined up at this point, but I will be doing my best to get one set up. So follow me on Twitter, again, at Meekins Lab, if you're interested in coming back. I try and have one pretty much every week, every Friday at the same time, 10:30 p.m. And I think that's everything I've got. So again, thank you all for coming out. Have a great evening, and be safe. Have a good weekend. Get your vaccine if you can, and wear a mask regardless. Thank you all very much, and I hope to see you next week.